Hey everybody. In DL3, we spent our entire class time focusing on FNTs. In this video, we're going to go over a couple of the FNTs to try to help you develop strategies for solving these kinds of problems when they arise. But before we do that, I want to make a comment about why we spent a whole DL on this. In physics, there are two main things that we're trying to teach you. The first is perhaps the most obvious one. We're trying to teach you physics. This includes all of the concepts that we'll be focusing on, such as conservation of energy, later conservation of momentum, and all these other physics-first ideas. But there's a second piece to this course, and that piece is problem solving. This part is much more difficult to teach, which is why we spend time in DL going over FNTs. One comment we often get from students is that when they take quizzes and tests, they feel as though they're being asked to do things that they never learned about in class. I can promise that we will never ask you to work with a physics concept on a quiz or a test that we have not talked about in DL and in lecture. What we will do, though, is give you a problem that you have not seen before that may require you to get a little bit creative with the way that you apply the concepts. All these problems are designed to be solved in a reasonable amount of time, so you should never be too concerned about running out of time when you're taking a quiz or an exam. However, if you do not practice your problem-solving skills now, it's going to be very challenging when you actually have to take these assessments. That's why working on the FNTs is so very important. They help you build your problem-solving skills so that when you do get to an assessment, you have the tools that you need to solve a problem that you have not seen. The best way to get good at this is just practice. So I encourage you, take the FNTs seriously. If you get stuck, maybe call up a friend and ask them for help. Work together to develop the techniques you need. With that said, let's go over a couple of the FNTs that we looked at in DL3 and see if we can work on building these problem-solving techniques. We're going to start out with FNT 7. Let's read it together. Imagine you are gradually adding heat to a 500-gram block of ice initially at negative 25 degrees Celsius. You can ignore the pot's thermal energy and assume all input energy is perfectly transferred to the water. One question that could be asked is, what is the final state of the water, phase and temperature, after the addition of 250 kilojoules of heat? Part A. Explain why, based only on the given information and without further analysis or calculation, it is not possible to construct a single energy interaction diagram that could be used to determine the final state of the water. Hint. Try to construct such a diagram. Explain why you can't. So let's do that. Let's try to construct a single energy interaction diagram for this problem. First, we have to ask ourselves what energy systems in this problem are changing. In this problem, we have a block of ice that is not at its phase change temperature. Because the ice is not at its phase change temperature, any energy we add will initially go to warming up the ice, increasing its temperature. So we know that there's at least one bubble for the thermal energy system. What about the bond energy system? Well, this is where we start to see the problem. In order for the bond energy system to change, we must first raise the temperature of the ice up to its phase change temperature, its melting point, which is 0 degrees Celsius. However, we do not know, based on this problem, what the final temperature of the ice is. We only know how much total energy we added into it. So it's possible that with this amount of energy added to the ice, we only end up with ice at negative 10 degrees Celsius. If that was the case, the phase would never change. However, it's also possible that by the time we warm the ice up to its melting point, we still have energy left over. If that were the case, the ice would then begin to melt, and potentially the liquid water would then warm up above its freezing point. So what can we do to try to figure out this problem? Well, the easiest thing to do is to construct sub-diagrams. In other words, to just take little pieces of the process and determine how much energy is required just for that piece. We can then compare that amount of energy to the total amount of energy that we're given in this problem, which is 252 kilojoules. And we can see how far that amount of energy will take us. The first sub-process we want to look at is the process that takes the ice from negative 25 degrees Celsius up to its melting point. Let's draw an energy interaction diagram just for that process. In this process, the only energy system we care about is the thermal energy system. And the process that we're looking at is the warming of the ice from negative 25 degrees Celsius to 0 degrees Celsius. This is the only bubble in our energy interaction diagram. Now we know this system must be open because we're adding energy to the system. The whole point of the problem is to try to figure out how the ice will change as we add energy to it. We also need to write in what our physical system is. We know that energy is entering the system, so we draw a little arrow here pointing in and write Q for heat. Our statement of energy conservation is fairly straightforward. There's only one energy system changing, and there's only one source of energy, the heat. So our statement of energy conservation looks like this. We want to know this number, which is how much energy we have to put into the system in order to raise the temperature of the ice from negative 25 degrees Celsius to its melting point, 0 degrees Celsius. So to do that, all we have to do is calculate this number, delta E thermal. So we expand it using MC delta T. Now we have to go back to the problem statement to find these numbers. The mass is 500 grams. Now note, when you're doing these problems, we cannot use grams as our units. We have to use kilograms. 500 grams is 1/2 of a kilogram. Next, we need C, the specific heat of the ice. It's not given to you in this problem, but you're not expected to memorize these. If you were to see a problem like this on a quiz or a test, you would always be given this number. It turns out that the specific heat of ice is roughly 2.1 kilojoules per kilogram degrees Celsius. Finally, we need the change in temperature. We know the change in temperature. It's 25 degrees Celsius. Recall that in this part of the problem, we're trying to determine the amount of energy it takes to warm the ice up from negative 25 degrees to 0 degrees, a change of 25 degrees Celsius. Now all we have to do is plug this into our calculator to try to determine this value. Plugging this in, I get about 26 kilojoules. Recall that a kilojoule is just 1,000 joules. So what we've just determined is that in order to raise the temperature of the ice from negative 25 degrees Celsius to 0 degrees Celsius requires roughly 26 kilojoules of energy. Let's go back to the problem statement and see if we have enough energy to do this. Well, the problem tells us that we have a total of 252 kilojoules. 26 kilojoules is definitely less than 252, so we have plenty of energy left over to start melting the ice. Let's now draw an energy interaction diagram for the melting process. Remember that during a phase change, the temperature of a substance doesn't change. It remains a constant. The only energy system we're considering in this part then is the bond energy system of the ice. Just as with the previous part, this is an open system because we're adding energy to the ice in order to melt it. We can now write down an equation just like we wrote down an equation in the previous part. The only energy system that is changing is the bond energy system, and the only source of energy is heat. So the equation looks like this. Let's expand this. First question, is this a plus or a minus sign? We know that when a substance goes from solid to liquid or liquid to gas, the bond energy is increasing. So we know we have to use the positive sign here. What about delta M? Well, we're trying to see if we have enough energy to convert all of the ice from a solid to a liquid. So let's just use the total mass of the ice for delta M here. Remember that in general, delta M might not be the total mass, but for this problem, we'll use the whole mass just to see what number we get. We may have to look up delta H for ice. It turns out that delta H is 333.5 kilojoules per kilogram. So the total amount of energy it takes to warm the ice up to its melting point and then melt it is 166.75 kilojoules plus 26 kilojoules. So it takes 192.75 kilojoules in order to warm the ice up to its freezing point and then melt it entirely. Looking back at the problem, we see that we still have some energy left over. There's a total of 252 kilojoules to go around, so we have about 60 kilojoules left over in order to now warm up the water. We could continue as we had before by calculating the amount of energy it would take to warm the water up to its phase change temperature, which would be the boiling point, and compare that to the amount of energy we have left. However, water has an extremely high specific heat. It is very difficult to warm up. So I highly doubt that we'll be able to warm up all this water to its boiling point using only 60 kilojoules. So instead, let's calculate how far 60 kilojoules can take us. We'll draw another energy interaction diagram just as before. We know its thermal energy will be increasing because we're warming up the water. Its initial temperature is 0 degrees Celsius, and its final temperature is unknown. This is what we're trying to find. Just as before, this is an open system with heat entering. Our statement of energy conservation is then delta E thermal equals Q. We already know Q. Q is the leftover energy that we haven't used yet, roughly 60 kilojoules. Let's expand the left-hand side as well. The mass is still 0.5 kilograms. The specific heat of water actually changes as the water changes phase. Liquid water has the highest specific heat, while solid and gaseous water have lower specific heats. What about delta T? Well, delta T is always just the final temperature minus the initial temperature. We don't know the final temperature, that's what we're trying to solve. But we do know the initial temperature, it's 0 degrees Celsius. All this has to be equal to the 60 kilojoules that we have left over. The only piece of this equation that we don't have is this T final. So using algebra, we can now solve for it. When I plug this into my calculator, I get 28.6 degrees Celsius. We've now solved this problem. By breaking it down into a bunch of steps, we were able to determine that the final state of this system is liquid ice at 28.6 degrees Celsius. This was essentially a bookkeeping problem. We had a certain amount of a resource, in this case energy, to spend. We were curious about how far that amount would get us. So we broke our process down into a bunch of smaller processes and asked, do we have enough energy to complete this process? Once we determined that the answer was yes, in the case of the warming of the ice to 0 degrees Celsius, we just went on to the next process and asked, do we have enough energy to complete that process? We continued down this road until we got to the end of our resources. We ran out of energy, and we were able to determine both the final phase and final temperature of our system. Now let's look at FNT 9. This one is slightly different from a lot of the examples that we've seen so far in that it involves a chemical reaction. In other words, a rearranging of elements from one set of substances into another set of substances. Our job is to figure out how much energy is either released or absorbed when this process completes. One way we can think about chemical reactions is as a sort of breaking apart and reassembling process. We begin with the reactants, in this case propane and oxygen. Our products are carbon dioxide and water. This is a process that you're probably familiar with, known as combustion, when we burn a substance to produce heat. So we expect that this process should release energy. Let's see if we can actually calculate how much that is. The easiest way to think of this is as if you're pulling apart all the individual molecules on the left-hand side and then reassembling them into the products on the right-hand side. Let's draw out what this looks like in an energy interaction diagram. We'll start with the first product, the propane. Because it's on the reactant side, we're pulling apart the propane into all its individual pieces. So does this involve an increase in bond energy or a decrease in bond energy? To figure this out, let's think for a moment about bond energies that we're more familiar with, particularly bond energies associated with phase changes. When water goes from liquid to gas, we say that its bond energy is increasing. We should also know that a gas is a gas because the molecules are not bonded together. Whereas in a liquid, the bonds exist, but they're a little bit weaker than in a solid. So we know that breaking apart of molecules corresponds to an increase in bond energy. So we should expect that the bond energy of the propane is increasing as we break it apart. How do we know that it's increasing? Well, the number of moles of this substance is changing. On the left-hand side, we have 1 mole of propane. And on the right-hand side, we have 0 moles of propane. So our initial number of moles is 1, and our final number of moles is 0. Next, let's do the same thing for the oxygen. Just like with the propane, the oxygen is being pulled apart into its individual atoms. So for the same reason that the propane's bond energy is increasing, the oxygen's bond energy must be increasing as well. Looking at the chemical equation, we can see that we start with 5 moles of oxygen and end with 0 moles. Now let's move on to the products. Our products are carbon dioxide and water. What's happening now is we're taking all the individual pieces that we pulled apart in the beginning and recombining them to form these products. As you might expect, because breaking bonds increases bond energy, forming bonds will decrease the bond energy. So we know that our products have negative changes in bond energy. We'll start with the carbon dioxide. Our bond energy is decreasing because we are forming bonds. There is no carbon dioxide on the left-hand side of the equation. Our final number of moles is 3. Finally, we'll look at the water. Just as with the carbon dioxide, our bond energy is decreasing. We start with 0 moles of water on the left-hand side and end up with 4 moles of water on the right-hand side. These are all of the energy systems that are changing during this process. Now, is this an open or closed system? We know this process is not closed because we're asking how much energy is released when this process takes place. So we surround this with a dotted line. We expect that energy will be leaving the system because this is combustion. Energy is being released. But if we didn't know this for sure, we can always do the calculation to determine it ourselves. Writing down a statement of energy conservation, then, we get the change in bond energy for the propane plus the change in bond energy for the oxygen plus the change in bond energy for the carbon dioxide plus the change in bond energy for the water all equals the amount of heat that is leaving the system. Now we're actually able to calculate how much energy is released. In part C, we're given the magnitude of the bond energy changes when these substances are formed. Now keep in mind, this is a magnitude. There are no plus or minus signs on these numbers. We have to put those in on our own. So let's start with delta E bond for the propane. The change for the propane is 402 kilojoules per mole. That means for every mole of propane we break apart, we have to add 4,002 kilojoules. We only have 1 mole of propane, so this turns into 1 mole times 4,002 kilojoules per mole. Next, we'll go to the oxygen. This problem tells us that the oxygen has a bond energy of 495 kilojoules per mole. We have 5 moles of oxygen, so our change in bond energy for the oxygen is 5 moles times 495 kilojoules per mole. Now we'll go on to the carbon dioxide and the water, but we have to be careful. Remember that these numbers in part C are only the magnitude of the changes. Just like with the bond energy system when we're talking about ice, for example, we have to include the positive or negative signs manually. We know that the bond energy systems are decreasing for the carbon dioxide and the water. So we know that we have to put negative signs on these numbers. This is why drawing a correct energy interaction diagram can be so helpful. It helps you avoid making little mistakes like not adding negative signs. We're forming 3 moles of carbon dioxide, and it takes 1,607 kilojoules per mole to do this. Lastly, we'll look at the water. Just like with the carbon dioxide, bonds are being formed, so we expect the change to be negative. We're forming 4 moles of water, and it takes 925 kilojoules per mole to do this. All this has to equal the heat entering or leaving the system. Now all we have to do is plug all these numbers into our calculator and determine the value. The number I get is negative 2,044 kilojoules. So the heat leaving the system is 2,044 kilojoules. I want to make a comment about this minus sign. You might be thinking to yourself, combustion makes everything really hot. Why did we get a minus sign here? Well, it's important to keep in mind what our physical system is. Our physical system is just the reactants and the products. It is correct to say that combustion tends to warm things up, but what it's warming up is the environment around the reaction. If you build a fire, you feel the heat being let off by the combustion. This minus sign just indicates that the products that are actually combusting are losing energy. That energy is then going out into the environment. It's what we would experience as warmth.